Dawudanepi, Tuya, Yuxatini, Yuhan, people of honor. My spirit is so happy to see you all. Karen, you do us up. My name is Karen. Grachish, Isa Afi, Grachish. Thank you so much for listening to my words. Thank you. Welcome, everyone. It's so good to have all of you here with us in our lovely Egan lecture hall. It's full. I love seeing all of you. As I said, my name is Karen. I'm the Dean of Arts and Sciences here at UAS, and so happy to be your host for our evening Egan lecture series. I want to begin tonight with our land acknowledgement. Our campuses reside on the unceded territories of the Akwan, Tontaquan, and Chieftaquan on Tlingit Ani, also known as Juneau, Ketchikan, and Sitka, Alaska. We acknowledge that the Tlingit people have been stewards on the land on which we work and reside since time immemorial, and we are grateful for their stewardship and incredible care. We also recognize that our campuses are adjacent to the ancestral homes of the Kradas and Tsimshian, and we commit to serving their peoples with equity and care. We recognize the series of unjust actions that attempted to remove them from their land, which includes forced relocations and the burning of villages. We honor the relationships that exist between Tlingit, Kradas, and Tsimshian peoples, and their sovereign relationships to their lands, their languages, their ancestors, and future generations. We aspire to work toward healing and liberation, recognizing our paths are intertwined in the complex histories of colonization and harassment. We acknowledge that we arrived here by listening to the people's elders, lessons from the past, and these stories carry us as we weave a healthier world for future generations. I'd like to recognize our Chancellor, Dr. Aparna Palmer. I had her in my sights before and then I lost her. Where's she? Those of you who don't know Aparna, please get to know her. I know that one of the things she really loves is getting to know as many members of the Juneau community as possible, as do I. We have a new provost this year who I saw walk in and start taking some pictures. Dr. Scott Billingsley is up at the top there. Hi, Scott. Scott's giving a little wave up there. Before we start tonight's lecture, I always like to give a little preview of our upcoming lectures, especially with a group like this, because I want you to know some of the other speakers that you have in store for you. So next on Friday, October 24th, we have a really cool lecture from Kevin White. So Kevin is a wildlife ecologist, and Kevin's going to do a lecture called The Ecology of Mountain Goats and Avalanches. Also, Eran Hood was involved in this research as well. And it's when Kevin talked about this, I thought it was so cool. He was talking about how mountain goats use steep, exposed terrain to avoid carnivores such as wolves, but there can be this really significant cost to this behavior, which is snow avalanches. So he's going to talk about this research, and if any of you are interested in that topic, I'd love you to come and engage with us on that one as well. And then next on Friday, November 14th, a new professor here, but also not new, because he started off as Eran Hood's student way back in the day as an undergrad here, and then went off and did his graduate work, and now he's back here as a research professor. So I'm super excited about that. He's a forest ecologist, and he's doing really exciting work. His lecture with us is called Arctic Ecosystems in a Warming World. So I've heard him speak, and I was really just taken away. He's been doing work with us at the Alaska Coastal Rainforest Center, and his name is Dr. Logan Berner, by the way. And so he's going to talk about what's happening right now with our Arctic communities. I'm not going to get super into it, but how rising temperatures are really causing trees and shrubs to spread across the northern landscapes. And then lastly, we always do a creative showcase. So Lily Hope, a few years ago, decided to call it, and I have to do it like Lily does it. She says it like this: Winter Fire Showcase. And that's how Lily likes to say it. I say that this year we got the band back together because a few years ago, it was myself and Lily and Ernestine Hayes and Emily Wall. We did a creative showcase together. And so that same group, we're all getting back together to do it again. So it's a really cool group of people, not me, but Ernestine Hayes and Lily Hope and Emily Wall. Let's come for them. So that is Friday, December 12th is Winter Fire Showcase. And that'll be our final evening at Egan. Lastly, before we begin, we would be able to do evening at Egan if it wasn't for my incredible staff in arts and sciences. So if you would help me by giving my staff the most incredible round of applause. Allison George, Dallas Fire. We worked really hard to make this happen. Now it's my honor to introduce tonight's speakers, UAS professors, Dr. Eran Hood and Dr. Jason Amundson. I have to tell you a funny story. Earlier today, I texted Eran and I said, Eran, you don't have bios on the website. How am I going to introduce you? And Aaron's like, yeah, you don't really have to. Just most people know us. Just like say we're working in the program on the environment. We've been studying the flood since 2011. I was like, that's it?
That works.
That's it? I mean, these two are incredibly accomplished scientists. As a scientist, I want to come out here, I wanted to brag about them a little bit, and Aaron's like, no, you don't need to do that. And so I said, what if I just made it up? I don't think you wanted me to do that either. So, oh, Eran, you should have given me a real bio. So I looked up a couple of fun facts about them. A little specifically, Jason is a professor of geophysics who started at UAS in 2011. I did find his personal website, which Jason, it's beautiful, by the way. I love the photo on there. He says that his research focuses on understanding the dynamics of tide water, glacial boundaries, and implications of glacier evolution. Jason, by the way, has done visiting researcher work at the University of Helsinki and Hokkaido University, among others. I started to count his publications on his CV, and I got tired. He had nearly 50 publications, at least that I saw on his CV. There's numerous grants that are supporting his work. And I know many of you know Dr. Eran Hood already. He's a professor of environmental science. He's a current department chair of natural science. On what I can find on this man's, he doesn't brag about himself a lot online. What I can find is he lists his research interests as watershed hydrology, aquatic biogeochemistry, alpine and glacial hydrology, snow hydrology, and snow chemistry. Eran started with us way back in 2002, right?
Yeah.
2002. He has dozens upon dozens upon dozens of peer-reviewed articles, book chapters, and technical articles. Again, I started to count. I got tired at around 60. Not to mention the many grants supporting his work. Let's just give a really warm welcome to Eran Hood.
I don't know if this, how does this work here? Is that good? Can everyone hear me?
Is that good?
Okay, I think I can project. Thank you, Karen. Appreciate the introduction. So Jason and I, we're going to kind of split the talk up. And what we're hoping to do tonight, I know a lot of you have seen different versions of this talk in the past, and we really want to focus on the research tonight and talk to you about what research that we've done to date, what we understand about the flood, what we've come to understand about the flood over the last now 15 years that we've been looking at it. And also look a little into the future and talk about some of the work that we plan on doing, not only at Mendenhall, but also how we might be able to sort of bridge this work to other places in Alaska. So I want to start off by being very clear that there are a lot of people who are contributing to this. I was actually going to switch the light. It's going to turn the lights in front. Dallas isn't here.
Six, right?
Was it 6? Might get slightly darker. There we go. So there are a lot of people who have contributed to the science of this. The MVP up there, Jamie Pierce, is sitting right over here. Jamie, yes, Jamie deserves a huge round of applause because he's the only one who has the technical mountain skills and technical science skills to put cameras and a laser in the basin that allow us to see everything in real time. A bunch of people at the Weather Service, Gabe Wolken at UAF and DGGS, a bunch of postdocs that we've had. Sean Fagan worked on the dashboard that many of you are familiar with. So there's a huge number of people that are contributing to this. We've also gotten funding from a lot of different agencies, and I would definitely highlight the Alaska Climate Adaptation Science Center because they're really the ones who have funded this from the beginning. They saw the importance and gave us the funds that we need to start a lot of the scientific data collection that we're going to show you here tonight. Okay, so I think everyone here probably has some idea what a GLOF is, but I want to just get us sort of all on the same page. So glacier lake outburst floods basically occur when a glacier in some way impounds water in a basin or an ice marginal lake along the edge of the glacier, and then that water is released either underneath the glacier, around the glacier, sometimes in front of the glacier as a flood. In this case, the Suicide Basin flood, we're dealing with a retreating tributary glacier. And so the Suicide Glacier is pulled back, right? It's left an over-deepened basin, and the main Mendenhall Glacier acts as an ice dam that impounds upwards of 16 billion gallons of water. All right, how did we get here? Well, this is, if we go back in time, we can see that Suicide Glacier was a very healthy glacier. It was adding ice. It was a tributary glacier to Mendenhall. You can see a medial moraine there, and all that ice is being added to the Mendenhall Glacier. And Christian Kienholz climbed up and took another picture from approximately the same location, and you can see that it's a very different landscape, right? The glacier has thinned tremendously. The Suicide Glacier is pulled back up out of the basin and left that over-deepened basin there, which is then walled off by the main Mendenhall Glacier. And so this is functionally the issue that we're dealing with, is that we have a very large, over-deepened ice marginal basin that impounds water each year. The basic mechanism through which these outburst floods work is that you fill water into the basin to the point where the hydrostatic pressure can sort of lift or force water underneath the glacier. And so you see the top there, the water's filling up, and then as it gets to a certain point, it's able to force its way underneath the glacier. And as it forces its way underneath the glacier, the flowing water in that conduit creates friction, which opens the channel wider and wider, right? So it's like if you pull the plug in the bathtub, and as the bathtub's draining, the drain hole is getting larger and larger. So it starts off quite slowly, and then as that conduit opens up, the water is released very rapidly down into Mendenhall Lake. So again, a lot of you, so here's the camera that Jamie put up here, and this is from 2024. I'd mentioned we haven't put together 2025 in a GIF here, but you can see it's filling through the summer, right? So we're in June, we're in July, we'll get into August here. And so you see the water level building and building and building, and then it's released very quickly, right? So that's the 2-day period roughly where that billions of gallons of water are released out underneath the glacier. And you can see the main filling point is in the back of the basin there, where there's a waterfall coming down from Suicide Glacier. Okay, so again, I think a lot of you are familiar with this, but just so we're all in the same place here, there's the glacier, the Suicide Glacier that pulled back, that tributary glacier, there's Suicide Basin. So we're not very far up Mendenhall, right, on the east side there. The flood pathway is underneath the glacier. Many of you probably noticed this year that there was actually a shift in the outflow in the lake from the east side of the lake to the west side of the lake. Right now it's over by toward the West Glacier Trail. Regardless, that conduit is going underneath the glacier and dumping that water into the lake. And then the flood zone is everywhere downstream from that can be inundated. We've seen a lot of change over the time we've been studying it. So this picture was taken in July 2011 on the first flood. And if any of you remember that, the river was going up and up and up, and no one knew what was going on. It was like, it was a sunny day. It was a beautiful day in July. The river kept going up. No one knew where the water was coming from. And so there was a group of us that got in a helicopter and went up, and we flew. This was the first place we went. It was like, oh yeah, there's where it started, right? You could see all the stranded icebergs. And so at that time, it was very hard to see the basin was holding water because there was a continuous ice sheet. The remnant ice from the Suicide Glacier was covering almost the entirety of the basin. And so there was a lake under there, but people didn't really see the lake. And so I want you to look here. There's a bedrock outcrop, if you can see it up at the top there. And then we're going to go forward in time. And this is the same basin about a week ago. Okay, it looks very different. We used to walk back and forth across it. We don't walk back and forth across it. And oh, by the way, there's the bedrock outcrop, right? And so what that shows us is that the water level used to be up there. And so that's really a clear indication of how far the main glacier ice dam has thinned since 2011. And in one way, we would say, well, that's great because the dam is so much lower, it can never fill up to where it filled up to before. But as Jason's going to explain and show you the math, that doesn't mean that the flood is smaller, right? We all know that the floods now are larger. And so there's other dynamics at play beyond just the thickness of the ice dam. Okay, looking down glacier, again, like drone's eye view here, you can see what we call the spillway, and we'll refer to this repeatedly in the talk. And this is the area where when the ice dam is over top, the lowest portion of the ice dam is along the margin of the glacier against the bedrock. And so many of you saw that huge waterfall that was out there coming down. That was water spilling over the top of the glacier along that spillway there. And so when we look at the overtopping point, we measure the highest elevation of the ice along that run against the bedrock there. And we look at how that's changing in time. And then in the bottom here, you can see the ice dam. All right, so one of the main tools that we have, if I can play my video here, is using drones. And so Christian Kienholz, who was a postdoc with us back in 2018, 2019, he started a mapping program in drones. And so basically, you fly a drone over the basin, and the drone has a pattern where it grids and it covers the entire basin. And basically, it just flies that gridded pattern and it maps the entire basin. It takes about 2,300 photographs. And if we zoom in on one of those grid lines, you can see that the photographs all overlap each other. And that's really important because every pixel in every photograph occurs in multiple photographs. And the drone, because of the accuracy of the GPS, we know exactly the position in space that it was when it took each photograph. And so then you can calculate the distance between the pixel and all the different positions where it was photographed, and that will give you the exact elevation of the pixel in space. And so it allows you, with just regular photographs, to create a 3D map. So we stitch all these photos together, and you can create what's called an ortho image. So it looks kind of like a satellite image if you see that, but that's just 2,300 drone photos taken from an elevation of about 350 feet above the glacier and stitched together. And the really important thing about that is that it allows us to make what's called a digital elevation model, right? And that's a 3D model of the basin. And because Christian started this in 2018, we now have dozens of images like this that can help us to understand how the basin is changing over time. So when you look from the back of the basin here, one thing that you can see very clearly is that on three sides, the boundary conditions are fixed, right? It's bedrock. And so Jason has a bunch of cool images to show you. And when he scrolls through them, everything that's bedrock is completely still in the images because it's not moving in time. But we have one side, the ice dam, which is changing very rapidly or dynamically, I should say, over time. And so the position of that, the thickness of that, and it's kind of like having your own tidewater. I mean, it's a lake having glacier up here in this side basin, because again, the bottom of that basin is downhill from the Mendenhall Glacier. So the Mendenhall Glacier, if you look at the ice velocity, it's flowing into the basin and it's created a steep calving face right there. Okay, so with the drone mapping, we can look at how the position of the ice dam changes. We can look at how the height of the ice dam changes. And then we can also look at the volume of icebergs, because it turns out that the volume of ice in the basin is one of the really important parameters that determines whether the basin is getting larger or whether the basin is getting smaller. So if we go back to one of the very first images that Christian took, again, you could see even in 2018, we could walk all the way across the basin, right? There's still this remnant sheet of ice there. The edge of the basin, what we'd consider the ice dam, was about there. At that time, we didn't quite realize how important it was going to be to look farther out. So Christian wasn't flying as far out as we fly now, because we didn't realize how much that front was going to move. So if we go forward to 2025, you can see where it was and you can see where it is right there, right? And so that gives you a sense of the calving front and the movement along the calving front in terms of the ability of the basin to start expanding laterally. You can also see very clearly that that remnant ice sort of sheet that covered the basin has completely disintegrated, to the point where I'll show you a picture in a minute of someone from the Army Corps of Engineers landed a helicopter in the bottom of the basin. So that is, that's kind of crazy to think about. All right, so this is what it looks like when it's drained, right? So this is about 2 weeks ago. And really, from a forecasting perspective, one of the most important variables is the shape of the basin, right? Because essentially, we think of this like, as a forecaster, you would say, this is a big bowl of water that's going to release. And if I know exactly how much water is contained in the bowl, that's going to make my forecast much, much better than if I'm trying to guess at the amount of water that's coming out. And I need to actually go out of, I have to go out of here to get this to work, which I think will work. So this, Sean created this for me. There's a 3D model of the basin, right? And so it gives you a sense of that we know the exact shape of every iceberg, of every rock. And so because we know the exact shape, as I'll show you in a minute, as you start to fill it, for any elevation of water in the basin, you can calculate exactly the amount of water that's being held in the basin all the way up to the top of the ice dam. All right, for some reason that doesn't seem to work. The 3D part of it doesn't. All right, so now we're gonna go and we're gonna think a little bit about what was different in 2025. And so we're gonna take a very short, maybe sped up helicopter flight on a foggy day when we almost couldn't take off downtown. And we're gonna fly over Mount Bullard and we're gonna see the basin the most full that it was this entire year. So the one thing I want you to notice here is that the waterfall there's a tremendous amount of water coming in, more than there usually is, because there was so much rainfall that preceded this event. So that's an important issue as far as what happened in 2025. And then if we keep going here, you can see basically looking toward the ice dam, it's full to the top, right? We just looked at the completely open ice dam there. And we said someone landed a helicopter, and actually the helicopter just like towed in and people jumped out. But regardless, you could jump out in the bottom of the basin, which I never would have thought of a few years ago. So in thinking about what was different about this flood this is a picture taken on that flight, and there's the, there's the top of the ice dam right there, right? It's full up to the top. And then when I show you the empty photo, you'll see like a 500-foot vertical cliff of ice right there that is holding all that water back. You can also see where the water used to go up there at the top, right? And so the water elevation is far lower than it was. The highest water elevation we ever observed in the basin was in 2016, to the point where the ledge where we do a lot of work, Jamie and I went out there and it's like, it was underwater. His coat was floating around. There was like stuff floating around. We're like, oh, we never thought the water would get that high, but it did. And the station with the camera and stuff was just barely above the water line. It will never be that high again because the glacier will never be thick enough for that. Again, the runway or the spillway along the edge there, when we landed, we could see there was no water in the spillway. And so we knew that the whole release had gone underneath the glacier, right? What sort of tricked us in this case is that there was so much water spilling over the top, we didn't realize at the same time it was also releasing underneath, because usually when there's no rainfall, the switch is like pretty clear. It's like, oh, it started to go underneath. In this case, the whole time it was overtopping, or a lot of the time, it was also releasing underneath, which is why initially the forecast was time shifted off of what it should have been. Maybe people noticed that it was like going to be later, and all of a sudden it's like, oh wait, we got to shift that back, because we didn't realize it's hard to pinpoint exactly when it starts flowing underneath. So if you look down, this is looking at the spillway, and there was a tremendous amount of thermal erosion, right? So you could put a person down in that hole because the water flowing down the side of the glacier was just eroding into that. And Jason has some super cool graphics of that. All right, so here's the last three floods. Now what's showing on the y-axis is discharge in cubic feet per second. So that would be stream flow in the river. These are detrended by taking out the base flow. So this is just the flow of the flood itself with the rain, like everything that was coming out of the glacier before, that was already there before the flood started, is removed. So the floods themselves are easier to compare. The caveat to that is it's kind of hard to know exactly how to remove the base flow, but as best the Weather Service could do it, it's removed. So you can see a couple things. From 23 to 24 to 25, the area under the curve is getting a little bigger, right? So that was saying the volume is larger over time. There was also a steeper rise to the peak this year, and that was something that we noticed pretty early on. It's like, oh, the water's actually releasing more quickly than we initially predicted. I'm saying we because the Weather Service actually has to predict this. So and so that was a little bit of a surprise. If we just pull out that 2025 flood and now we compare it to the river, right? So now I put the rain and everything else, the melt, back in there. You can see that typically the stream flow in Mendenhall River is about 3,000 cubic feet per second that time of year. And so it was above 9,000 cubic feet per second. So that tells you it started at an elevated point, right? But because the effects of that rainfall, it was coming down from the rain flood. And so on the back end here, you see it goes down to a lower point there. And so this is basically like the rain bump. So it got an initial rain bump, and that contributed that there was just added water in the system. And that's part of what resulted in that higher peak. There's also potentially a sort of dynamic feedback associated with that. And so here's just a gratuitous photo of standing in front of the basin when this was like mid-July. So it's getting pretty full, but it's not that full yet. That rock where I'm standing would go underwater eventually. So the other feedback that we think might be at play is if you see this cartoon and you're forcing water under the glacier, well, the growth of that conduit at the bottom where the water is being released is a function of the pressure, how much pressure there is on it and how long it's exposed to that water pressure. And so this year, because there was so much rainfall coming in, it kept the flow and it kept the water level in the basin higher, which we think might have given more time to widen the conduit out. And that could create like a faster run out of water from the basin. We would love to see the conduit, but I don't know if you see a conduit anywhere in the ice dam there. I don't see one. I see like a little lake in the bottom that's left over. I see like a 400, almost 500-foot tall wall of ice. This is like if you had a tidewater glacier and you drained the fjord. That's what it looked like right there, which is weird because you don't get to see that very often. But regardless, we can't see the conduit. If we go over to Tulsaquah, we can see the conduit in Tulsaquah. It looks like a subway tunnel, right? You can see the conduit because look how thick the ice is right there, right? We also know at Mendenhall, because the ice is so thick here, that soon after it drains, the conduit, the overburden closes the conduit because we saw it refilling, right? We had a second event after the first event because the conduit closed up and the basin partially refilled. This one, because there's not very much ice above it, it's not closing up, at least right here. And so you can look at it and say, oh, I wish we could see, I wish ours looked like that, but it doesn't. So, okay, a couple more points, then I'm going to hand it off to Jason. Kind of what some of the things that we're thinking about. If we go back to the original one, we had a continuous sheet of ice and we had a tall ice dam and we had this conduit which forms when it releases. As we go forward in time, the ice dam is thinner and then the ice sheet is disintegrated, right? And so again, these are all the factors that are changing the volume in the basin. From the drone imagery, we can also track the elevation of the ice dam, and spoiler alert, it's getting shorter because the glacier is melting. So that's in our favor as well. This is what's called a volume elevation curve. And this is like the secret sauce that the Weather Service is using to forecast the flood. They make a different curve every year. And this curve is from that three-dimensional bowl that I showed you. And all it says is, if you tell me the elevation of the water in the bowl, the water in the basin has an elevation of, like, you can read it off the laser online and say it's at what, 1,200, 1,300 feet. You just read across on the curve, and that will, if I can find my cursor here, and then you read down, and it gives you the volume. And of course, it's an acre feet because it's the US government, and that's what, an acre with a foot of water. So, I mean, at that level of water, no unit is relatable, so we'll go with acre feet. So basically, you can just read off, and that's exactly like right there. It's like, okay, that is the exact volume of water held in the basin if you know the spillway elevation, right? And we know the spillway elevation from the drone imagery. And so you just pick it out there, and then that's your volume. Once it starts spilling, you just like, I have the number and I need to make a curve, and then I'm good to go. What you'll notice here is that this is shifting right and downward. What that means is the dam is getting lower and the volume of water stored is getting larger, right? We only can do this for 3 years because the basin never fully drained before 2023. So we don't have like a full basin bowl volume before 2023. And so this is kind of like this process of the basin changing over time is exactly what we're trying to look forward and understand into the future, because conceptually, the life cycle of these things, which last for decades, right, should look something like this. It should start off with nuisance flooding. There's a ton of ice in the basin. There's an ice sheet. It can't be that big. And then it starts going up. The ice is melting. The basin's expanding. There's some point where it reaches its maximum size, and then the ice dam is going down, and eventually the ice dam is gone, and then it goes to zero, right? And so what we're trying to figure out is, like, did we have these 3 floods? Did we have those 3 floods? Like, we're somewhere up the curve. Hopefully we're up near the top of the curve. We don't know yet. But that's kind of like, those are the dynamics at play. And Jason's going to talk now about like all the things we're studying to look at sort of where we might be on this hypothetical life cycle curve for the outburst flood. So with that, I'll pass it off to Jason.
Great. So it might not be a surprise that the peak discharge from these floods scales with the volume. And so I just wanted to show first a graph. This also comes from the Weather Service of all of the floods that have been recorded at Mendenhall, including a bunch of small ones that most people weren't paying attention to, the ones you see on the lower left. But basically, as you have more water released during a flood, you're going to have a higher peak discharge. It's not a perfect fit because there's some mechanics, there's some variability from year to year related to how the flood releases. But fundamentally, if we want to be able to understand how these floods are going to change over time, we really need to know the volume of that basin and how it's changing. So I'm going to go into a little bit more detail than Eran did about how we go about calculating that and what some of our estimates are at the moment. I'm also using acre feet. Weather Service uses it. It's actually kind of a nice number. If I express this in gallons or like cubic meters, it's like billions of gallons. So these are actually kind of nice numbers to move around. A football field is about an acre. An acre foot would be if you put 1 foot of water on top of a football field. It'd be pretty close. So yeah, we want to understand how is it changing at present, and then later I'll talk a little bit about how we're going to try to understand how it's changing in the future. So the things that affect storage capacity, Eran already mentioned. The basin shape is really important. The height of the ice dam, the location of the ice dam, and the volume of floating ice. And drone surveys are really a great tool for this. They can provide us all that information and more. And we've done almost 50 surveys now since 2018 and plan to keep doing it for the foreseeable future. I'm going to show a series, or I'm going to show a bunch of what we call hillshade DEMs throughout my part of the talk. A DEM, again, is a digital elevation model. So think of it as a topographic map. And then the hillshade means you take that map and you shine light on it so that it has shadows and makes it look three-dimensional. The thing I really like about the hillshades is that they don't have the same issues with lighting that you have when you look at the photographs, because it's really consistent lighting from one scene to the next. So what I'll do first is I'll go through the series of DEMs that we created this year. And I wanted you to notice 3 things. The thing you're going to notice first is number 3. You're going to see the basin filling up and then draining. That's really pops out at you. I also want to point out that the bedrock doesn't move at all, that the data is like really pretty amazing. And it's nothing to do with mere Eran. It's just that the technology that is, I mean, serious. It's like you just collect this data and you put it into some software and then you get this really amazing product out of it. And so because the bedrock isn't moving, you can see the glacier moving and you can also track that. You can figure out how fast is the ice flowing in different directions. Okay, so here we are, June 10th. I'll just step through these and I'll go back and forth a few times. Right, so we can see it filling up July, getting very full. This is shortly before the flood, and then this was after. And then Eran was up there a couple of weeks ago and did another one. Right, so I'll just go back and forth a little bit. If you just look at the bedrock around the basin, it doesn't move at all. There's actually a couple spots where on the lower right where there's it's like there's loose rock and stuff that moves around as the runoff is changing into the basin. And then especially between, let's see, this one and the next one is huge amount of movement of the glacier into the basin. Part of that is that it's a longer time period, so the ice had time to flow farther. But part of it is also that you have this huge cliff that Eran was talking about. This is something that's really rare in nature, to have an ice cliff that's, what did you say, 500 feet tall? So when there's water in the basin, the water is pushing back against the ice and affecting how fast it can flow into the basin. But once it drains, you have this huge cliff and it wants to just ooze into the basin really quickly. So it's just from like a purely ice dynamics glaciology perspective, it's a pretty interesting thing to look at. There's a lot of other things we can see that some of it is fun, some of it is useful. The first thing I'm going to show is just kind of fun, and it gives you a sense for like how good this data is. I'm zooming in, and this is kind of the southern part of the basin. And that thing I circled there's a little dot, that's a rock, probably this big. And when I step through the images, you can see it melting out and then starts to fall down. All right, again, the bedrock to the side of it isn't moving at all. You can also see little rocks moving around kind of on the slope there. Right, so I think that's just illustrates how good this data is. We can also see things like the amount of erosion of that spillway that Eran was talking about. You can see icebergs that get transported into that spillway and then melt over the course of a month and a half. So let's see, here is the DEM that we produced on August 13th, the day after the flood. And there's a transect, a red line right there is showing, I'm going to show some elevation profiles from that transect, but you can kind of see where just in that area, how there's a bit of a channel that's carved into the landscape there, into the glacier. Before I show the profile, I'll just show a photo from August 13. You can see some icebergs stranded up on top. So it's clear that the water was up at that point. You can also tell the ice is really white and clean. And just up above that, there's a lot of rock and debris. The ice surface is much rougher. So there was quite a lot of water flowing through here. And then if we look at a surface elevation profile, we see this. So this is the left side would be like towards the middle of Mendenhall Glacier. The right side here where it's really steep, that's the rock face. It's about 100 meters across. And the red profile is from August 6th. The blue one is from August 13th, right? So if you're walking from left to right, you would basically be walking like kind of down the glacier towards the slope here. On the left side, you see that there's about a ½ meter difference between those two curves, and that's basically just due to surface melting. The glacier melts at something like 5 centimeters, a couple of inches a day in the summertime, depending on temperature and so on. But that change that you see over there is a function of surface melting. On the right side, the lines match up really, really well. That's because that's bedrock. It hasn't moved. There's one little kink there. I'm not quite sure what's going on, but mostly it matches really well. And then what I wanted to point out is here at about 90 meters, where did the cursor go? Oh no, I see it's over there. Okay. At about 90 meters on this transect, there's a big difference between the red and the blue, and that's where the spillway is. So there's something like 4 meters of erosion that happened in maybe a day or two. I'm also going to point out some icebergs. These are icebergs that got that flowed over the spillway, and then as the water drained, they got left in place. They don't look that big compared to some of the other ones that we were seeing in the DEMs, but they are actually quite big when you're there in person. I also circled some others that are just stranded on bedrock. So this is August 13, and I'll just go back and forth. This is now September 30th. So those icebergs all disappear. And to give you a sense of scale, here's a photo that Eran took on that, I guess it was when you went up, right as it was starting to drain. You can see some of the icebergs sitting there. And then on August 13th, we were back walking around. So these are the small icebergs that got pushed over to the spillway. But what really amazed me is that by the end of September, they're basically gone. So there's enough surface area, high enough melt rates that those things all melted away or almost entirely melted away. Okay, so back to the real questions though. How is the basin storage capacity changing at time? Again, it depends on the ice dam elevation, the amount of floating ice in the basin, and the ice dam location. I'm going to present things in acre feet. It's a volume. For context, the 2025 flood released about 51,000 acre feet, and that's actually about 57% the volume of Mendenhall Lake. If you look at a map, you wouldn't guess that because Suicide Basin looks a lot smaller, but it's also much deeper. Mendenhall has a couple of spots that are 80 meters deep or so, but most of it, especially the part like by Skater's Cabin and such, is fairly shallow, whereas this is just a really deep basin. So first I will talk about the lowering of the ice dam. Eran talked about this a little bit. He had a plot that showed the ice dam elevation over time. I'm just going to show some transects. So along this line right here, the left side of the image will be onto the glacier, and the right will be towards the rock face. And then these are I guess 6 different years. So the black line is 2020, and then 21, 22, 23, 24, 25. And what you see is that as you go from one profile to the next, there's a change of a few meters from one year to the next. So this means that the ice dam has thinned something like 15 to 20 meters in the last 5 years. Take that and you multiply by the surface area of Suicide Basin, and you get something like 8,500 acre feet. This means that the storage capacity of the basin has reduced by about 8,500 acre feet because of ice dam lowering. But that's not the whole story. As Eran was saying, it also depends on how much ice is in the basin and where is the dam located. So another thing we can do with the drones is we can get a pretty good estimate of the amount of ice in the basin at any point in time, as long as the icebergs are floating. Because we know that 10% of an iceberg is sticking out above the water and 90% is below. And there's enough spots where there's water exposed where we can pick that and get the elevation. So we know the water elevation. We can compare that to other locations where we know the surface elevation of this big iceberg, for example. You can use that then to calculate how much ice is in the basin at any point in time, do this several times and get an idea of how much change has happened. So from 2020 to 2025, we lost about 12,000 acre feet of icebergs, and that increases the storage capacity. So that number is bigger than the amount that we lost due to the ice dam lowering. I guess I should also point out that the DEMs are also a really nice check on our other measurements that we have for monitoring the basin. We have a lidar up there that Jamie Pierce has been maintaining, which has been super helpful. But the problem with the lidar is it's pointing at the basin, but it's hitting icebergs. And so when icebergs move around, you can see this thing jump around. So this is our DEMs are just another check. Every couple of weeks we can go and we get a surface elevation from these and we can compare it to the DEMs. Okay, so then the third part is this issue about the location of the ice dam. Here I have two DEMs, post-drainage DEMs, one from 2020, one from 2025. It's hard to tell here. If you flip back and forth between them a little bit, you can see that the dam in 25 is a little bit further back than where I would mark it in 2020. And we also now have a pretty good idea of the shape of the basin. So if you take that amount of change and you account for the cross-sectional area, you can come up with an increase in storage of about 6,400 acre feet due to this thing retreating, or retreating into the main part of the Mendenhall. I have to say this is probably the hardest part of the problem is even just identifying where is that boundary, and also thinking about how is that going to change in the future, because this has to do with some pretty complicated ice dynamics related to fracture and icebergs breaking off and things like that. So I think this is probably the hardest part of the problem. Here I have taken two DEMs, again, one from 2020 and one from 2025, and just taken the difference from them to calculate thinning rates. Ignore the part here in the middle where it's dark red, because these DEMs didn't have the same water elevation. They were just, what I was really focusing on here was the change in the glacier elevation. So in the area of the spillway, this sort of medium red color, that's about 15 to 20 meters of thinning that have happened. That's mostly a climate signal. And where am I going? Up here, this area where it's dark red, just upstream from the ice dam, that's about 40 meters of thinning. Twice as much thinning happened there. And that has to do with ice dynamics. You have this huge cliff, the ice it wants to flow into the basin because you have this huge unsupported cliff. So the ice speeds up, and when it speeds up, it thins. It's like stretching taffy or something like that, right? And so even though the basin has it's only retreated maybe 100 meters or so in the last 5 years, I think that maybe the concern and the challenge is with this amount of thinning, we don't quite understand what's going to happen in the coming years. Let's see. Okay, so you put these numbers together, and I should emphasize these are pretty preliminary. They still have some large error bars, but this at least gives us an idea of how we're doing. So the change in volume is the reduction in floating ice increases the volume, basin expansion increases the volume, and then the ice dam thinning lowers it. Add those numbers together, subtract the ice dam thinning, and I get about 9,900 acre feet. Which if you compare that to the 2025 flood volume, it's about 20%. So this suggests that in the last 5 years, the storage capacity has increased by something like 20%. A little bit scary to think about it continuing to increase 10,000 acre feet every 5 years. But I think the thing that should give you at least a little bit of comfort is that there's not a lot of floating ice left in the basin. If I just go back really quickly to here. 2020, we had 18,000 acre feet. 2025, we had 6,000. This 12,000 acre feet of iceberg melt, that was a major driver of basin expansion over the last 5 years. And with only 6,000 acre feet left, it's hard to imagine that we're going to gain a lot more capacity, storage capacity through iceberg melt. So, but I think the wild card is sort of what's going to happen with the ice dam location. Yeah, and so that leads us into what we're trying to do in the future. So thinking about how the basin storage capacity is going to change. I already said I think the iceberg melt is going to start becoming insignificant in the near future. And so then it really becomes a question of thinking about how quickly is the glacier thinning and is the basin going to expand further into the glacier. So I just want to talk real briefly about some work that's in progress. It's not very far along yet, but the idea is to do some modeling of glacier evolution. This is a model I set up of Mendenhall with some really poor bed topography. There's some work that people have done to try and construct bed maps of glaciers around the world using some pretty I don't know what the word is, but they're making some assumptions that are probably good at sort of a regional scale, but when you go and look at individual glaciers, you see that the bed maps are not very good. So with that caveat, I used an existing bed map, spun up a glacier model using the bedrock topography of Mendenhall and surface topography. You can see what's plotted here is the surface velocity. This red here would be an ice fall that's coming from Suicide Glacier into Suicide Basin, and then the Mendenhall Towers would be right here. So this was done sort of more as just a proof of concept. What we really need is better bed topography. And then to run the models, we need climate projections, which we have with some uncertainty associated with those. And then we have some observations of glacier surface velocity and thinning rates that we can use to help tune models. And so this expected products we will get out of this would be the lifespan of Suicide Basin, how fast is the glacier thinning and retreating, and then also some idea of the variations in the potential flood volume, because by knowing what the glacier surface elevation looks like and where the boundary of the glacier is, we'll be able to say something about how that basin is changing over time. So we are working on collecting ice thickness data. This is what I'm going to show you is hot off the press, or not even off the press. It's just hot off that instrument. So we have a radar. Gabe Wolkin at UAF has been doing this work for us. Has a radar that we fly, basically looks like a sling load. A helicopter flies a grid, and that is transmitting electromagnetic waves that penetrate through the ice. Some of them will bounce off the glacier surface and come back. So that tells us where the glacier surface is. Some of them will penetrate all the way through to the bottom of the glacier and bounce back. And so on the left there is a map of Mendenhall with the grid that they flew, I think he said they did about 75% of it. Once they got up into the higher elevations, the data deteriorated a bit, but all of the lower elevations from, do you remember what elevation it was?
1,200 meters.
So everything from 1,200 meters down has been flown on that grid. And then the right here is showing what the data looks like. It hasn't been fully processed yet. So right now it looks like there's this really sharp V-shaped valley, which is not what I expect to see in the end once it's fully processed. This is a transect basically near Suicide Basin. It goes from, I guess, the North Star Trekking has a camp somewhere in here. And then I lost the cursor somewhere here. And then it goes across over to Suicide Basin. And so you can see there's a really strong reflection at the surface. That's the glacier surface. And then there's some strong reflections at the bottom, which appears to be the glacier bed. And so Gabe's estimate from a quick look at this is that the glacier in this spot is about 600 meters thick. I think the surface elevation there is 500 something. So that would suggest that this is below sea level, that's pretty impressive. It also actually, if you go back and look at Roman Motika's work from the early 2000s, this is totally consistent with some of the things he had done. He didn't have as much data as we have, but he had some radar data that suggested that the bed was going to be below sea level. So it looks like the glacier is retreating out of Mendenhall Lake right now, but I expect at some point in the future there'll be another lake further upstream. All right, so now once Gabe is able to take this data, finish processing it, we'll have a nice bed map, and then we'll use that in our glacier simulations. So I would say at this point, we have a really good grasp of the basin volume and how it's changing over time. I would say we have a pretty good understanding of the flood mechanics, though we don't understand all of the year-to-year variability. partly because it's really hard to observe the conduit and how that changes over time. But from sort of a forecasting perspective, with this catalog of events that we have and just a record of how fast the basin fills and drains, I think we have a pretty good understanding of that aspect. And then this new data that we have will allow us to model the evolution of the glacier into the future. Eran and I were involved in a study with Mike Heckers, I think it was about 5 years ago now, where we were working with some architects that were helping to redesign the visitor center, and there was this whole study that was done. We did a really crude model of the glacier, trying to estimate how it would thin. They wanted to know at what point in the future would you no longer be able to see the glacier from the visitor center. So this was just an example of the sort of product that we produced from that, using a model that was probably not good enough for peer review, but I think it was good enough to like conceptually understand how the system would change. And so I think this data that Gabe has collected for us is going to be really useful for a lot of things, not just, I mean, obviously for the work we're doing on Suicide Basin, but also just having this really great information on the glacier and thinking about how that's going to change going into the future and what sort of impacts that might have on the landscape and the hydrology of the whole Mendenhall Valley. Okay, before we wrap up, Eran wanted to say just a couple more things.
One quick plug on. So I think most people are familiar with the dashboard that we have, like the Juneau flood. We're building a new one that's going to be for the whole state. And so this map, it's not up yet, but when it is up, it has a map of every identified ice marginal lake in the state. And so you could like click and zoom in and see like everything that looks like Suicide Basin all over the state. We identified ones that have impacts in red. So you could click in and you can learn like about Valdez Glacier, Suicide Glacier, or Ski Lac, or Snow River Glacier. But what we're really hoping to do with this, Jason and I have a project that's funded by the National Science Foundation. If you look at the legend in the bottom, there's like an orange diamond, and there are none of those on there. And that's because someone that we're working with at Carnegie Mellon, who does like kind of global glacier modeling, is going to model all the glaciers in this picture and use that to predict where all the new suicide basins are going to occur. Because looking back, we should have known this was going to happen, but we didn't. And so all the other places where it could happen in the future, the modeling that we'll do will help to inform people to say, hey, watch out in 30 years if you live downstream of this, because it looks like when this side glacier detaches, there's a chance that you might have a situation like this. And then they can, you know, on this, we're also linking to some of the stuff on our website. So it's like, here's what could happen. And anyway, just to kind of give people a heads up for that. So that's one thing that's coming. We're going to release this dashboard this fall, even though it won't have the other stuff for like a year or two more, just so people can learn statewide about where these things are and what else we know about them. And then the last one is just a request for everyone here that's interested. So the Juneau flood dashboard that we built last year, which has the flood maps and a bunch of other stuff, we'd really like feedback on that, because we know that people used it. It got how many thousands? It got about 15,000 page views the first day of the flood, and like something like 6,000 unique users in one day. So it's like, well, people are looking at it. That's a good thing. But it didn't really tell us what they thought of it. Interestingly, more than half the people looked at it on their phone, which makes sense if you're like walking around trying to figure out what to do or whatever. So we would love, if you are interested in the flood dashboard and you have opinions of it, this Sunday at the Valley Library, I will be there with some other people. And we're just like, if you have comments, we'll just talk about what we're trying to do with it. And we'd love to get feedback. If you don't want to come to the library next Tuesday night, we'll be on Zoom, and you can show up on Zoom and say like whatever you want. Like, can you do this? Can you do that? Can you, you know, whatever. And so anyway, that's just like, if you're interested in the flood dashboard and you're willing to give us some feedback, we'd appreciate it, because it's for you. And so if you help us get feedback, we can make it more useful and better for you in the future. So if you click the QR code, will give links to the feedback. And And you can also with Juno, it's on the Juno Flood website too. There's like a pop-up now. It's like, come help us out. And if you go there, you can find that as well. So we'd love it if people here would give the time to give us some feedback so we can make this better for you. And with that, I will stop talking finally, and we would be happy to take any questions about anything except HESCO barrier.
Wilson and I both have mics. We wanna, if you have a question, I've got the first one over here. We're gonna ask you to ask your question on a microphone so that the people on live stream can hear you. So I'm gonna hand you a microphone.
You can talk.
The first forecast was remarkably accurate. The second one dramatically not so. What's the difference?
I would say the short answer, and this is because Aaron Jacobs called me today and he's like, someone's going to ask you that question. I think the short answer is that the assumptions about the way that water's released are based mostly on the full basin scenario. And so the same kind of thing happens. Like if you guys notice you get those emails or on the website, the Weather Service website, like as soon as it reaches a certain level, they start to say, if it released today, it would look like this. If it released today, it would look like this. It's challenging there because you have to use like a forcing, and the amount of pressure forcing when it's full is different from when it's partially full. And so part of it is like, well, it's always better to be like a little overestimating, but when you use we don't have a good library of curves for like partial fall releases. And now that we have a couple of them, they'll do a better job. Just like in 2023, we didn't know it could drain to the bottom, so there was no way to forecast that. And so part of it's like understanding that second release, which is not a full release, has a different rate of release, and getting some data to help tune that in. So the short answer is it's different. It's like going to be a different set of curves, and it will get better.
I've got a question here, and then Allison's got somebody.
I wondered where the icebergs are coming from. Is it just the breakup of the old ice sheet of Suicide? Is there falling from Suicide Glacier down the cliff? Or is it falling from the ice dam of?
Probably all three. There's definitely iceberg. So I'm not so sure about how much ice would be falling down from Suicide Glacier. That's probably a pretty small amount. I suspect there's still some ice left over from remnant ice from Suicide Glacier when it was down there. But we definitely know that there are icebergs calving into the basin throughout the summer. And actually what happens, I think as the basin fills up, you start to see that part of the ice on the Mendenhall Glacier gets lifted up a little bit, and then it breaks off. And so you see through the summer that ice dam retreats back a little bit. It doesn't really, in the short term, it doesn't have any effect on the storage capacity because you've just taken some icebergs that were attached to a glacier and put them into the basin instead. So that doesn't really have much of an effect. And then once the basin drains, then that ice dam re-advances. So it's kind of like Eran was saying, it's a bit like a tidewater glacier, that you have icebergs that are ice that's flowing into the basin, icebergs that are breaking off, and then you have this boundary that moves a little bit. And we didn't show it here, but we have actually Crane Johnson, who's at the Weather Service, had done this. He had calculated the volume of icebergs for almost all of our DEMs, or at least the more recent ones. And you could see that actually through the summer, there was more floating ice in the basin than there was earlier in the summer, because it had calved icebergs and the ice had retreated back the terminus.
Yeah, and one other just quick point. One of the interesting thing that happens with that calving is that some of the ice breaking off has actually been held underwater, right? And so there's this buoyant pressure upward. When it snaps off, it actually comes up out of the water. And we were there one time when that happened, and all of a sudden these icebergs are flipping over, and the ice popped up, and the whole water level in the basin dropped, right? Because it released the ice that was underwater, so it actually created more storage instantaneously by snapping off. And so it's super dynamic. And then we were like, oh, it's draining, oh my God. And then we came to our senses, we're like, it's not draining, what are we doing? It's go get the GPS at the water line, we're running around. So
this actually shows it really well. July 14 to 22nd, you can see there's a pretty big iceberg in the
Yeah, up in the top there.
right here. This gets pushed way down because there's another iceberg that pops off.
Yeah, so that you can see all that ice that we were standing right on the ledge
So this is all new.
right there. And that popped off and everything started like going bonkers. And anyway, so it can actually create volume by releasing ice that's like being held down underwater, and then it pops up, and then the bathtub ring like drains down a little.
You have a question over here?
Hi, also an iceberg related question.
Yeah.
Jason, you said that icebergs played a huge role in the difference in storage capacity that you saw this year, but that you don't expect that to be the case in the future. Can you explain that, please?
Yeah, so the point there was just that in the, I was going to try to find the numbers. In the last, so in 2020, there was about something like 18,000 acre feet of ice in the basin, and this year there's now 6,000. So there's only 6,000. We lost 12,000 in 5 years, but there's only 6,000 left. So there's not a lot more ice to be melted away.
Which is why you can also land a helicopter on the bottom of the basin now, right? Because there's areas that are ice free. And I don't know what, I had a great picture of someone standing in the bottom of the basin, but I lost it. And I was really upset because I went with these guys and they dropped me off to fly the drone, and then they decided to land down there. And the helicopter couldn't stay there. So the helicopter came back and I said, why did you come back? He said, oh, they wanted to go down. I was like, what? They went in the bottom and they didn't take me? Like, why am I up here? This is their first time here and they get to land in the basin?
But
But they're also the ones that have to fix the problem. So they should be in there looking around.
the reason I started my data here with 2020 was because prior to 2020, like 2019, 2018, it's a little bit harder to tell what is floating and what's not because things haven't broken apart yet. So we have, from 2020 onward, I have quite a bit of confidence in how much ice there, how much volume there is stored in icebergs. But some of our estimates from 2019 and 2018 suggest that there was something like 25 acre feet of icebergs. And so this is the main way that you gain storage, it seems, is that you melt the icebergs. And we've melted a pretty large chunk of that over the last 7 years.
I got you got a question right here?
Yes. My question is about the radar scanning you're able to do of the bedrock. So I know you have the models. Are you finding that there's additional potential lakes in the ice field?
Oh. Yeah, kind of anticipated that. So I mean, the main thing that we have been worried about is, let's see, would be this basin right there, at least in the shortish term, like 50 years time frame. I haven't seen that data yet. Gabe told me that it didn't seem to be that deep. And it's a little bit hard to imagine that it could be as deep as as Suicide Basin. I mean, to be able to produce those cliffs in such a deep basin like you have at Suicide Basin, you need quite a lot of ice to be flowing through there. So at one point in time, the Suicide Glacier must have been contributing a lot of ice through there and eroding bedrock. If you look at this basin, I keep losing the cursor. If you look at this basin off to the west, there's not really a source for much ice. So this ice that's up there is not flowing very fast. It's probably not eroding the bedrock that quickly. So I'm a little bit skeptical that it could be a big basin. We're not sure yet because we haven't fully processed the data. I think further into the future, there's other spots that could be, once you get up into here, you could imagine like this part maybe detaching and or something like that. But that's, at that point, we're talking about maybe 100 years from now. But anyways, we hope to have some better answers about that in the next, I don't know, few months or so.
Yeah, I mean, Gabe, like specifically, we pointed him toward that and they flew the helicopter in there. So that was like the key question we wanted to answer.
We'll take a few more questions. Allison's got one over here, and then I see this down here.
The release in 2025, would you consider that to have been a fast release? And do you anticipate any way in the future to predict that, or is it just as it comes that we'll find out?
I think the main answer to that is that it was a fast release, the fastest release we've seen in terms of just the rate at which the amount of water in the river was increasing hour over hour. Interestingly, when we plotted that, like the rate of rise, like how quickly is the stream flow changing, that actually peaks several hours before the river itself peaks. And we were doing that through the night this year, plotting it. So we figured out that's actually a really good diagnostic tool because the rate of rise is going up. In other words, like 1 hour to the next, it's like, 2000 CFS, 2500 CFS. It's like going up, up, up. And then it peaks. And now we know, oh, wow, when we see that rate of increase turn over within 3 hours, the flood peak is going to occur. So that's going to help even from a diagnostic standpoint more. I think we've it's really the Weather Service forecasting. We have a good library of curves that they can use, and you can really see where it's setting up relative to the past curves. And that's why it's like so important to look back and see, like, because there's sort of the initial plot, and then you have to look and see how you're doing and like make tweaks to it. And I think like after everything was tweaked this year, it was like pretty much spot on in the end. Like it hit pretty much right on there. So could it get faster? Sure. I think most of the worst case scenarios involve very large rain events. And we, a little bit were in luck this year because there was just enough offset between the two where like the rain event lifted up flow and the flow is actually coming down as the peak of the flood was going up. And so if they had been more synchronous, we would have seen a higher flood peak. Like it probably would have gone to 17 feet or above if those two events had lined up perfectly, but they didn't line up perfectly. And that also, as I mentioned, Eran said, tell people how hard it is to forecast it when you put the rain. He was calling like a dirty hydrograph was his term for it. And it's like, it's so much nicer when it's sunny and it's just like the same amount of flow. And then it starts like that and you can see exactly what you're dealing with instead of it already being up and coming down and then trying to figure out like that. So that was the trick. One other point I wanted to make just about Jason's comment, and this is something Jason and I've talked about a lot, going back to this sort of curve, we're reliving a lot here, this curve here, thinking about the life cycle, like we had a student that Jason worked with who was modeling, made an outburst flood model that was very theoretical a few years ago, but what it showed is that the peak of the flood should occur about the time that the basin becomes ice-free for the exact reason that you're asking is like that you've sort of maximized volume. And then at that point, in theory, the ice dam lowering should overwhelm the other forces. It's never that clean. And I made this like to show that it's like not ever going to follow the curve exactly. So because we're down to only the 6,000 acre feet, theoretically, that's kind of a good sign that we could be nearing the peak. But again, I think a lot of it has to do with like the dynamics along that ice wall there. And then also just like fingers crossed that we don't have an atmospheric river at the same time, because obviously that could change the dynamics, having nothing to do with the outburst flood, really.
Here, a basic question, why is the word Yakalop unfavored?
Because it's way too hard to say. It's a glacier outburst flood.
I have a comment I'd like to make on behalf of many people here. I can't thank you and everyone enough. Our property was flooded this year on River Road, and your modeling and everything you've done is super. Thank you.
Yeah.
I think that's just a really great way to end our Q&A session. I know that Eran and Jason will probably stick around for a couple minutes. I know there's other people who may have questions. I also want to thank both of you. Like, what a fantastic talk. And thank all of you for coming out. We really appreciate you engaging with us. We always want to see our community members come out to UAS. So please come out for the next one. We'd love to see you here if you have another question, I know that they'll probably stick around for a couple minutes.
And-
Again, thank you, thank you.
And don't forget to come and give feedback. And even if you just want to come and ask questions, that's fine too. I'll talk about even not the dashboard, if you want to just ask questions. So,